Welcome to the Problemers channel, season 3, episode 23, the episode which I titled the Shunting Yard algorithm and its slow motion player, because in this episode we will discuss how a computer science algorithm can be animated and visualized by the means a graphical user interface program. But before we deep dive into the underlying computer science of the current problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on our channel and use the comment section to that episode that may be of interest to you. And we also recommend that you do not undervalue the significance of the so-called season guides, the free PDF files, in which I have indexed all the episodes on this channel and all the problems that we have solved on this channel so far. And these season guides are a way to get a quick and convenient at a glance view of all the problems that we solve on the channel. And of course, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. The objective of the problem S3CS5 was to explain in your own words the inner mechanics of the Shunting Yard algorithm, and most importantly, create an animation or a visualization of that algorithm that allows user to witness the inner mechanics of that algorithm in the front and center fashion for the following two reasons. Reason number one, in animation and or visualization of computer science algorithms is a pursuit that is worthy in its own right, because as animals we are quite visual. We consume the bulk of our daily information visually through the optical nerve. As such, when we see how certain things work, that witnessing of the process may help us deeper understand that process, and as a side effect, it may also help us either improve the existing algorithms or perhaps even invent new ones, related or unrelated. And number two, the very process of animating or visualizing a given computer science algorithm is an ultimate test of our understanding of how such an algorithm works. Because if we do not understand how this or that algorithm works, then there is absolutely no chance that we can animate or visualize that algorithm in any reasonable way. And conversely, if we do understand how this or that computer science algorithm works, then it is not really a guarantee that we will be able to animate and visualize it in a reasonable way. Originally, the Shunting Yard algorithm was invented or designed by the gentleman named Dijkstra, who was a theoretical physicist by training, in order to evaluate the values of finite, arbitrarily parenthesized expressions that are arithmetic in nature. The expressions that are shown at the top of the board over here and arbitrarily parenthesized means that the location of the parentheses in such an arithmetic expression is not known ahead of time. However, it turns out that even though the Shunting Yard algorithm is not very complicated on one side, but is quite sophisticated and elegant on the other, it punches way above its weight because with minimal effort, the Shunting Yard algorithm can be adjusted to work on expressions that are not arithmetic in nature. For example, with minimal effort, the Shunting Yard algorithm can be adjusted to work with the so-called Boolean expressions that are shown in the middle of the board. And the idea over here is the following. Such a Boolean expression can be considered a template or a rule, if you will, and through that rule that can be pre-compiled ahead of time into an executable form, a body of text can be trolled, and the result of trolling a body of an arbitrary text through such a Boolean rule or a Boolean template will be either true or false. For example, let's say we pulled a paragraph of text from a random website, for example, and then we troll this paragraph through the Boolean expression shown over here. Then let us pretend that this body of text has the words pork bellies or the words orange juice, and it does not have the words crude oil in it. Then the result of the evaluation of this body of text through this expression will be true because this body of text satisfies this here template or this here Boolean rule. And conversely, let's assume that the paragraph of text that we're trolling through this rule does not have the words pork bellies. It does not have the combination of words orange juice, or it does have the combination of words crude oil. Then in that text we will fail that paragraph saying that this body of text does not satisfy this here Boolean rule or Boolean template, and this result of the evaluation of a given paragraph against the given rule evaluates to false. Likewise, with minimal adjustment, the Shunting Yard algorithm can be used in order to compute and output the derivatives of a finite composition of differentiable functions, or let's say elementary functions, the functions whose first derivative is known ahead of time. For example, we can have a hairy expression as shown over here, the natural logarithm evaluated at the trigonometric function of sine, which is evaluated at the trigonometric function of sine, which is evaluated at the trigonometric function of tangent, which itself is evaluated at the point, let's say 17x. We also, as humans, we all know how to compute first derivative of such compositions, but in this particular case, this task can be automated using precisely the Shunting Yard algorithm. But in this episode, our emphasis and our attention will be on the arithmetic expressions or expressions in the shape shown at the top of the board over here, and we will be preoccupied with figuring out how the value of such an expression can be computed. The first-class citizens of the Shunting Yard algorithm, as it was originally designed to process arithmetic expressions, is a finite, arbitrarily parenthesized arithmetic expression, and arbitrary means that neither the number or the location of the parentheses, which override the default order of execution or that override the default precedence of the underlying arithmetic operators, is not known ahead of time, nor the number of the arithmetic operators themselves is not known ahead of time. As such, neither of this information can be encoded with variables and the operators in the programming language of choice, and as such, this problem needs to be solved in a generic way, and such a way is the Shunting Yard algorithm. Now, an operator in general is a call to action, let us do something, and an operand or an argument to the operator is the fodder for that action. Popular arithmetic operators are addition, designated with the plus sign, the additive inverse, known as subtraction, designated with the minus sign, multiplication, multiplicative inverse or division, exponentiation, and the modulus operator. And with this quite shallow menu of operators, it is already possible to achieve quite reasonable and quite serious goals. Every operator, whether arithmetic in nature or not, has a property called the arity, which is the property that defines the number of operands or the number of arguments that the given operator acts on. All the popular arithmetic operators that we will be working on, addition, subtraction, multiplication, division, exponentiation, and the operator of modulus, or the operation of taking the modulus, are binary operators because they require precisely two arguments to work on. But if we extend the vocabulary of operators and agree that, for example, factorial, designated with the question mark, for example, 5 factorial, is yet another operator, then this will be an example of a unary operator that acts on or requires only one argument or one number to act on. Likewise, if we extend our vocabulary of operators some more, then pretty much any real-to-real single variable function, such as our beloved, for example, cosine of x, the proverbial variable, then can be treated as a unary operator, or an operator that takes precisely one number to work on. And if we know the, for example, the Taylor series expansion, x to the power of 2n divided by 2n factorial, then we know how to evaluate such a function and compute its value. And the reason we will need arity is the following. When we pop the arguments of the operators in the Shunting Yard algorithm during the second processing stage, we need precisely to know the arity, or the number of arguments that such an operator acts on. If the arity of the current operator is binary or equal to 2, then we evidently will pop 2 arguments, or we will execute 2 pops of the operand stack. And if the given operator is unary, then evidently we will execute only 1 pop, and we will pop 1 argument from the argument stack. It turns out that there exist 3 distinct geometries which lock in the mutual juxtaposition of an operator with respect to its arguments, and these 3 geometries are described by the following 3 words: infix, prefix, and postfix. In the infix geometry, or in the so-called infix notation, the operator that is binary, and the reason we discuss binary operators is because all the arithmetic operators that we will be working with are binary. Such an operator is located in between its arguments. A typical expression here will be 1 plus 2, and in this case it is even possible to assign meaningful location qualifiers to each argument. For example, the argument 1 will evidently be the left argument of the operator addition, and the argument 2 will be the right argument of the operator addition. In contrast, in the prefix geometry, or in the prefix notation, the operator is located in front of, before, or to the left of its arguments, as shown over here, plus 1, 2. Evidently, it should be understood that the sequence of symbols 1, 2 does not represent one number 12, but represents 2 distinct tokens. As such, we have the implied, or if you will, here I showed explicitly the divisions between the input tokens, the token plus, the token 1, the token 2. As such, in the prefix notation, one more time, the operator comes first, if you will, and the arguments come after it. And lastly, in the postfix geometry, or in the so-called postfix notation, the operator is located behind, after, or to the right of its arguments. And using our example, the infix notation 1 plus 2 will be rendered in the postfix notation as follows: the token 1 followed by the token 2 followed by the token that designates the operator. Addition captured with the plus. The difference between these notations is the following. Inasmuch as the infix notation is human friendly, it is computer science or computationally not friendly. And conversely, both prefix and postfix notations, inasmuch as they are human not friendly, they are computer science or computationally friendly notations. And the reason for that is the following. If, and we will talk about this in a second in the next segment, every arithmetic operator has the so-called precedence, and if in an expression we want to communicate our ideas and our intention clearly to the audience and state that the lower precedence operator has nonetheless to be executed first, we use the so-called original order of execution modifier, or parentheses, or brackets. And by so doing, we exactly communicate the idea that the lower precedence operator, the operator addition, must be executed before the higher precedence operator multiplication. And such a construct is required for the infix notation. In contrast, the reason why the prefix and the postfix notations are computationally friendly is because they do not require the original order of execution modifiers, or the parentheses, in order to be executed. They are, let's say in plain English, parentheses free, no matter how long, no matter how involved or seemingly complicated or complex either one in notation, the string captured in either notation gets, in the prefix notation or postfix notation. That string of symbols can be evaluated without the use of brackets and without any special pre-processing. In addition to the property of arity, each operator, whether it's arithmetic in nature or not, also has another property called precedence. And precedence is a property that was designed in order to assign the order of execution to an operator when two operators collide. A collision of two operators is the mutual juxtaposition of two operators with respect to an operand when one and the same operand can be bound or assigned to two different operators at once. For example, in a simple arithmetic expression 1 plus 2 times 3 minus 4, we have, for example, the collision between the operator addition and the operator multiplication, because one and the same argument 2 can be equally bound or assigned to the operator addition, which thinks that 2 is its right argument, and at the same time the number 2 can be bound or assigned to the operator multiplication, in which case the multiplication operator thinks that 2 is its left argument. In order to deal with such conundrums or such conflicts or collisions, the notion of precedence of an operator was introduced, and across the popular arithmetic operators, we have it that the operator of multiplication, multiply and divide, and when it comes to these guys, the exponentiation takes precedence over the operator addition and subtraction. And the reason or the place where the precedence of operators is needed in the Shunting Yard algorithm is during the first stage, when an infix expression is parsed or transformed into either a prefix form or into the postfix form, and that is precisely the subject that we will talk in a few seconds. In addition to the properties of arity and precedence, each and every operator, whether it is arithmetic in nature or not, has another property called associativity. Associativity of an operator was introduced in order to assign the order of execution to the operators when two operators of the same precedence collide. We already know what a collision of two operators is. It is such a mutual juxtaposition of the operators when they share one and the same argument, or such a mutual juxtaposition of the operators and its operand, where the operand can be equally bound to one operator or the other. For example, in the simple expression 5 minus 2 plus 3, the operand 2 can be bound to the operator minus, or it can be bound to the operator plus with equal success. We do not really have any communication to us in this expression which operator should be acting on the argument 2 first. And in order to deal with these situations, the so-called associativity of operators was introduced. One more time, it is important to understand the associativity comes into play when two operators of the same precedence collide, not when the two operators of different precedence collide. Then the property of precedence takes over. So here in the expression above, the multiplication is executed first. 2 times 3 is 6. Then we add 1 to the 6, 7, and then we subtract 4 to add 3. But this brings us to the associativity of the operators as such. When two operators of the same precedence collide, then the way to resolve such a collision or conflict is by using the associativity of the operators at hand. And the associativity of operators comes in two flavors. An operator can be left associative or left recursive. Likewise, an operator can be right associative or right recursive. If an operator is left associative, then in a string of collisions, such operators are grouped from the left. If the operator is right associative, on the other hand, then in the collision of such operators, the operators that are right associative or right recursive, they are grouped from the right. For example, all the popular operators in the arithmetic world, addition, subtraction, multiplication, and division, are left associative. That means that as we read our arithmetic expression from left to right, we execute left associative operators left to right, or we group them from the left, which means that first we translate this expression into the one shown over here. Implicitly, we have the parentheses, which tell us that across two operators, the leftmost one should be executed first. That what means, that is the meaning of left associative of left recursive, which means 5 minus 2 is 3. 3 plus 3 will be 6, which is very different from the case if we were to execute the operator addition first. In this case, we would have to put 2 and 3 together first, obtain 5, and then from 5 we subtract 5 and obtain 0. 0 is not 6, 6 is not 0. That's a big difference. As an example of a right associative or right recursive operator, we have the operator of exponentiation. For example, in the expression 2, operator of exponentiation 3, operator of exponentiation of 4, what do we have? Well, we have the collision of two operators of the same precedence over the argument 3. 3 can be bound to the left exponentiation operator, or 3 can be bound to the right exponentiation operator. So which operator should be executed first in this case? Well, because exponentiation is the right associative or right recursive operator, it means that we parse such an expression from right to left, or we group these operators from the right. That is the meaning, which means that in this case, in the absence of any clear communication of the intention of what should be carried out over here, we have this configuration over here. So we first raise 3 to the power of 4. We execute the rightmost exponentiation operator first. 3 raised to the power of 4 will be what? 3 squared is 9. 9 times 9 is 81. 3 to the 4th is 81. So the result of this expression is 2 raised to the power of 81, quite large number compared to 1. And it is important to understand that in this case, it is not equal to number 2 raised to the 3rd power first, which is what? Which is 8. And then 8 raised to the power of 4, which is 64 squared, or 4096. It is important to understand that by default, the associativity of operators kicks in the absence of precisely that, the brackets or the parentheses, which are original order of execution modifiers. And now that we understand the properties of arity, precedence, and associativity, we can move on to the next step. In general, the Shunting Yard algorithm operates in 2 distinct stages. In the stage number 1, or in the first stage, the input infix expression, or the input material that is supplied in the infixed form, is converted into either a prefix form or a postfix form. Which form do you choose depends on you as a programmer. You decide. Basically, it could be your arbitrary decision. Maybe you carried out some more computer science analysis and you discovered that the time complexity of, for example, prefix notation or postfix notation favors you in your particular case, or the decision which form should be the material given in the infix form precompiled into can be dictated by external requirements. It doesn't matter, but fundamentally, stage number 1, infix is converted to either prefix or postfix form. In the stage number 2, the Shunting Yard algorithm carries out the execution proper. In other words, in this stage, the Shunting Yard algorithm will process the material that is already folded into the prefix or postfix form, whatever it is. This result becomes the input for the second stage, and this is done in order to compute the result, whatever the result may be. Now, the underlying mechanism which makes all this beautiful stuff happen is the tandem of 2 fundamental computer science container types, a stack and a queue. And these 2 containers are actually used with respect to the operands and operators in 2 different ways. In the first stage, when the material that is given in the infix form is converted into either the prefix or the postfix notation, the operands go onto the queue right away, but the operators go onto the stack. And the reason for that is because a stack is precisely a mechanism which is used to change the order of execution of arguments, or the operators. And the mechanics over here is the following. When we look at the current operator that comes from the material given in the infix form, we look at the precedence at the operator that sits at the top of that stack, and if the precedence of the current operator that comes in from the input queue is lower than the precedence of the operator that sits on top of that stack, we pop the stack first, we grab that operator, we push it out into the output queue over here, prefix or postfix form, and only then we bring the input, the current incoming operator, onto the stack. Evidently, I mean, it should be pretty obvious why we do that, because the higher precedence operator should be executed first. And the distinction between two stages is quite explicit, and no one says that these two stages have to be fused together. In terms of arithmetic expressions, most of the time they have to be fused together because it is difficult to templatize, even though perhaps sometimes it's possible, in which case, by all means, it is possible to split these two stages in time. And in my professional experience, when I was implementing a flavor of the Shunting Yard algorithm, then I would execute the stage number one at the program startup once and parse all the material that is given in the infix form into either prefix or postfix form and store that material in the precompiled form. And then at runtime in the real-time path, I will only execute the stage number two and process the incoming material against the precompiled prefix or postfix templates. And now that we understand that the Shunting Yard algorithm operates in two discrete or two different stages, let us look at the mechanics of the stage number one. As I mentioned before, during the first stage of the execution of the Shunting Yard algorithm, the tandem of the fundamental computer science container types, a stack and a queue, are used in the following way. The arguments of the operators or the operands go directly onto the output queue, while the stack is used to play games with the order of execution of the operators. And in the second stage of the execution of the Shunting Yard algorithm, the roles of the containers are switched around, and during the processing stage or during the actual computational stage, the Shunting Yard algorithm will use the stack to store the operands or the arguments of the operators. But here we will discuss the very first stage of the execution of the Shunting Yard algorithm, during which the material that is given in the infix form is precompiled into either a prefix or a postfix form. And if you're new to this, this will be confusing. If you have any more questions or if anything is not clear, then I have a link to a very detailed explanation of how the corresponding code that handles the operator's precedence and associativity can be written. Do not worry about it at the moment. Here, perhaps the most important thing for you to grasp is the following. During the conversion process of the material given in the infix form, when we compile this expression into the prefix form, then we read from the input and we write to the output in the right to left fashion, as shown with this arrow, right to left, starting with the rightmost position of the input. Conversely, when converting the given material in the infix form into the postfix notation or into the postfix form, we read from the input and write the output in the left to right, in the opposite direction, left to right, starting from the leftmost position. And the algorithm that actually does this is quite elegant. I have a full description again in the link that is in the comment section. But for a simple computation, let's say the material that is input into the Shunting Yard algorithm for the stage number one is given in the infix form, and it has the following shape: 1 plus 2 times 3. Then in the prefix form, this material will have the following shape. Again, if we read it left to right, it will be plus 1 times 2, 3. And it is quite straightforward to understand how this notation was generated. Like I said, in this case, we read the input and generate the output in the right to left fashion, starting from the rightmost position of the input. So here we go. 3 is an operand or an argument. We write it into the output right away here, logically the first position. Then next comes the operator. We technically push this operator onto the stack. This is the algorithm of stage 1. The stack is empty, there is nothing there, so we push the operator multiply onto the stack. Then we see the next token, which is an operand or an argument 2. So we write it to the output queue right away. Again, right to left, remember, 3, then 2. Then we come to the operator, which is the operator plus. Remember, in the first stage, the stack is used for the operators, and in the second stage, the stack is used for the operands. So here in the first stage, we're about to push the operator plus onto the stack, but this is the crux of the algorithm. Before we push the incoming operator on top of the stack, we have to check the precedence of the operator that sits at the top of the stack currently. If the precedence of this operator that sits on top of the stack is higher than the precedence of the incoming operator, guess what we have to do? That's right, we have to pop that higher precedence operator off the top of the temporarily operator stack and push it into the queue. So here we go, 3, 2, push, write the operator multiply over here, and then we push the operator plus onto the stack that is right now has only one operator plus. Then we have the last token in the input. It's an argument, so we write it down. We will push it into the queue right away, no thinking. So we have 3, 2, multiply 1, and now we pop the operator stack. The plus comes off, and boom, voila, we have our prefix notation, the equivalent rendering of the material in the infix form in the prefix form. Likewise, we work with the postfix notation when we take our material given in the infix form, 1 plus 2 times 3. The postfix processing requires us to do what? We read the input left to right, we write the output left to right. Again, 1 is an argument. Write it into the queue output starting from the left. Wonderful. Next goes the operator. What is it? It is the operator plus. The stack is empty, so right now the stack, let's say like this, we'll display it like this. At the bottom, we pushed it over here. Let's say our stack is. Next comes the token 2, which is an argument. Since it's an argument, we write it down to the queue right away. So next token is the operator. What is the precedence of the operator multiply? Well, it's higher than the precedence of the operator that sits on the stack right now. We have the only one. So we write down our operator, we push it onto the stack. So our stacks look like this. Stack looks like this. Operator multiply, operator add. Then we see the next token, 3. What do? We write it down, we push it to the output queue right away. And now, once we reach the end of the input, no more tokens, what do we do with our stack? Well, we empty it into the queue. Pop once. The operator multiply comes off, nothing here. It goes into this position in the queue. Pop one more time, the plus operator, and voila, we are done with the postfix notation. Likewise, in order to make sure that you understand how these things work, let's say we have the infix, the material that is given in the infix form. Now this time it's similar, but it's now parenthesized. We use the order of execution modifiers, the parentheses, in order to communicate the idea to the reader that, hey, the plus operator, the lower precedence operator, has to be executed before the operator multiply. Well, then the prefix notation, the equivalent form of this input material in the infix form, in the prefix form will be what? Well, if we read it right to left, it will be 3, 2, 1 plus multiply. If we read it left to right, it will be multiply plus 1, 2, 3. Again, if you're new to this, this will be a little bit funny, but that is what it is. And again, it will be clear why we write things this way in the second, once I explain how the second stage of the Shunting Yard algorithm works. The actual computation, in this computation, we will be pushing these numbers onto the stack this time in the second. So our stack will be, by the time we come to the operators, our stack will look as follows: 1 on top, 2 follows, 3 follows. Once we come to the operator, will be plus we will pop one operator left, the second pop goes right in the prefix notation, 1 plus 2, we execute the operator, take the result, push it onto the stack, and we roll forward. Now, the same material in the infix form, parenthesized 1 plus 2 times 3. In the postfix form will look as follows: 1, 2 plus 3 multiply. Again, make sure you understand. I recommend that you go through the same steps, reading this input left to right. And if you have any questions about how do we algorithmicize the handling of the parentheses, I explain it in the printed material, the link to which is in the comment section. Click on it, free website, no registration, no accounts, no nothing. Just go study this material. And in order to perhaps give you a real test, here we have a theory expression that looks as follows. I think I have one extra parenthesis. We do not need this one. 1 plus 2 times, open paren. 3 plus 4 times, open paren. 5 plus 6 times, open paren. 7 plus 8, close paren, balancing with this one, closing paren, balancing with this one. So how do we obtain the prefix and the postfix forms of this material given in the infix form? Well, this will be the expression in the prefix form: plus 1 times 2 plus 3 times 4 plus 5 times 6 plus 7, 8. And the equivalent material rendered in the postfix form will look as follows: the numbers, the tokens, 1, 2, 3, 4, 5, 6, 7, plus times, plus times, plus times, and plus. Count the number of operators: 1, 2, 3, 4, 5, 6, 7. And what do we have here? 1, 2, 3, 4, 5, 6, and 7. So it looks like I didn't make any mistakes, but do keep me honest. Verify, and here you have an opportunity to compare the prefix notation with its postfix counterpart. See which notation makes sense to you, which you prefer in vacuum, and try to explain to yourself why. Here we see that the postfix notation tends to cluster all the operands on one side and operators on the other, when the notation in the infix form is like this. But in the prefix form, it is not the case. We have the operators and operands sprinkled across the entire expression. But once you fight the fight with the prefix and the postfix notations and you understand how these things work, you can move on to the second stage, during which we will take our precompiled expression that is already given in the prefix form or in the postfix form, and now all we have to do is algorithmicize the process of evaluating these expressions in the prefix form or in the postfix form. During the second stage of the Shunting Yard algorithm, we process the precompiled expression, whether that expression is in the prefix or postfix form, directly without paying attention to the parentheses, because there are no parentheses in these precompiled expressions. Remember that the material given in the prefix form is processed right to left, starting from the rightmost input position, and the material given in the postfix form given in the is processed left to right, starting from the leftmost position. And the reason I use the humorous take on the famous Latin saying "Veni, vidi, vici," I came, I saw, I executed, is because the reason all this business of converting the material given in the infix form into either the prefix or postfix notation is that here is where we tactically win. Why? Because the physical location of an operator within the prefix or postfix expression is precisely equated to the order or the moment of its execution. And that is where I took this somewhat humorous take, "I came, I saw, I executed" idea from, because once we parse the expression given in the infix or given in the prefix or postfix form, the moment we encounter an operator, that's it. At that moment, we're executed, and then we push the result back onto the argument stack. Either this form is prefix or postfix, it doesn't matter. What is important to understand here is the following. As we process the material given in the prefix form or postfix form, right to left or left to right, if we encounter a token that is an operand, then we push this operand onto the stack. And once we encounter an operator, then this is the signal for us to start using the material that is accumulated on the stack. And if the operator is binary, this is where the arity of an operator comes in. You see where the operator is binary. Or, for example, your operator could be tertiary. It may require 3 arguments or maybe 4 arguments or whatever the case may be. You need to carefully roll this implementation over here at this point. If your operator is binary, you have to pop more than 1 argument. And that means that now we need to be careful with the specific location or the geometry, if you will, of the arguments as such. If the notation, the precompiled notation is prefix, then the first pop will produce the left argument and the second pop will produce the right argument. This should be evident by my helpful example over here. In the prefix form, we parse the input right to left, so we see the number 3, we push, so the stack looks like 3. Then we see the next token 2, we push, 2 sits on top of 3, we see the operator. So now we need to, the operator multiplication, it's binary, requires 2 arguments, so we pop 2 from the top, 2 goes left, the first pop. The second pop, we pop 3, it goes right, 2 plus 3, 2, 3 argument, the operator execute, take the result, push it back onto the stack. Now, if the precompiled material is in the postfix form, then the first pop will produce the right argument and the second pop will produce the left argument. This is where the distinction between these two forms, precompiled forms, becomes evident. Again, it should be very straightforward to understand, because if the material is given in the postfix form, we process it the left to right, starting from the leftmost position. So let's say here we have numbers go onto the stack. Push 1, push 2, push 3, an operator. So at this point, what does our stack looks like? 1, below 2, below 3. So 3 sits on top. Once we pop 3, 3 goes where? 3 goes to the right, and then the next pop, 2 goes to the left. So the first pop produces the right argument, the second pop produces the left argument. Once we have these arguments at hand, we come over here, no matter how we deal with the precompiled expressions, and then we basically execute this operator. We have the left argument, we have the right argument, we know what the operator is. Usually here you will have a very lengthy chain or string of if operator equals blah, do this, else if operator equals something else, do this. So this is also straightforward. Once you execute this operator, you will get the result. You take the result and you push it back onto the stack. And now that we more or less understand the essence of the second stage, the stage number 2 of the execution of the Shunting Yard algorithm, we can take a look at a couple of sample computations. Let us now carry out a sample computation for a given material in the infix form that is based on the prefix notation. We more or less understand how to produce this notation. So the expression in the infix form, parenthesized 1 plus 3 times 5, will be taken into the prefix notation that looks as follows: multiply, sum, 1, 3, 5. We know that this material we parse right to left, starting from the rightmost notation. Technically, what we have over here is tokenized input, token. I do not want to clutter this material too much, but this is what we have. So processing this material, the prefix notation right to left, we see the first token, which is what? It is an argument. What do we do with the arguments in the second stage of processing? We push them onto the operands or argument stack. So right now at the top of our stack there sits number 5. Then comes number 3, argument, push it onto the stack. So now our stack looks as follows. Next token, 1, argument, push it onto the stack. This is what our stack looks like right now. This is the top. This is, let's say, this is the bottom of the stack. Also, next token, it's an operator. What type of an operator? Binary. That means that we have to pop 2 arguments from the stack. Remember that according to our algorithm, if the notation is precompiled notation is prefix, then the first pop produces the left argument. Is that the case? Well, evidently in the infix notation, 1 is the left argument, 3 is the right argument. So in this case, we pop 1 goes left, 3 goes right, 1, 3, and the current operator that we took from the input is addition. 1 plus 3 is equal to 4. So what do? The first pop emptied technically the stack. The second pop emptied the stack some more. So now we have 5 at the top of the stack. Once we produce the result, we push it back onto the stack. So we write 4 over here, and we continue processing the input. Our stack looks as follows at the moment: 4 at top, 5 at the bottom. The next token is an operator. What type of an operator? Binary. How many arguments do we need to pop off the argument stack for the binary operator? 2. Remember again our template. The first pop produces the left argument, the second pop produces the right argument. So technically this is a stand-in for 4, left argument, 5 is the right argument. So here we pop 4 goes on the left, 5 goes on the right. The current operator is multiply. 4 times 5 is 20. So once we pop all this material off our stack, the stack is empty right now. We push 20 back onto the stack. So here we have 20. We reach the end of the input, nothing more. This is another, I gloss over all sorts of error handling because then we will get bogged down with the details that are not really relevant. But here at this point, once the expression was in the correct arithmetic form, the parentheses were balanced, everything makes sense. It's a nice, clean, correct arithmetic expression. At the end of the computation of stage 2, there should be only 1 entry at the top of the stack. Once we push this, once we pop that number, this is the result, 20. So now here with confidence, we claim that the value of this expression given in the infix form is equal to 20. Let's memorize this result and undertake a similar computation when the intermediate or precompiled form is in the postfix notation. Let us now carry out the same sample computation, but this time by precompiling our material given in the infix form into the postfix form. And before we do that, I would like to impress it onto the minds of our viewers one more time. Why are we fighting all these prefix and postfix battles? The reason why we fight the prefix and postfix battles is because by translating the material given in the infix form into the material that is rendered or precompiled into either the prefix or the postfix form, we gain the following competitive advantage. The physical location of an operator within the prefix or postfix form is equated exactly to the moment or to the order of the execution of that operator. There is no need for parentheses, the order of execution modifiers in the prefix or postfix form. And in this case, we know that when the material is translated into the postfix notation, we process that material left to right, starting with the leftmost token of the input, and in this case the leftmost input is 1. Again, I can try to tokenize this if you guys can see it. I do not want to mess things up too badly, but essentially this is what we have. The first token is 1. We push it onto the stack. This is what our stack looks like. The second token is 3. It's an argument, it's an operand. We push it onto the stack. So now we have 3 on the stack. This is our stack. This is what our stack looks like. The top of the stack, the bottom of the stack. What is the next token? It's an operator. What type of an operator? What is the arity of this operator? The arity of this operator is 2. The operator is binary. We need to pop 2 arguments. Here again, we need to be careful, specific locations, but because the notation is postfix, the first pop produces what? Produces the right operator. So in our case, this is our stack. The first pop, I'm sorry, this is already inertia. The first pop goes to the right and the second pop goes to the left. So now we have 1, we have 3. Our operator is plus. We know how to carry out this operator. This is equal to 4. Once we popped 3, this is what our stack looked like. Once we popped 1, the stack is now empty. We produced 4. We push 4 back on to the stack. This is what our stack looks like. We keep processing. We already threw out this token. We're done with it. The next token is 5. What is it? It's an operand or an argument. So what do we do with arguments? We push them onto the stack. So now this is what our stack looks like. 5 on top, 4 on the bottom. Let me erase this arrows because they're confusing now. What's the next token? Operator. What type is it? What is the arity of this operator? The arity of this operator 2. The operator is binary. We need to pop 2 arguments. The first pop goes right. So the first pop produces 5. The second pop produces the left argument. This goes here, 4. This is 5. The operator is multiply. We know how to multiply 2 numbers. 4 times 5 will be 20. Once we do the pops, the stack is currently empty. We push 20 back onto the stack. This is the only number. The expression is correct. There are no syntax errors. Everything is wonderful. Once we are done with the input, no more tokens, we go back to our stack. We pop the sole entry. At some point, this is our validation. If the size of the stack is 1, things are good. We pop the last and the sole element from the stack. This element is 20, and again we obtain the result which reads 20, coincides evidently with the previously computed result when we compile the infix material given in the infix form into the prefix notation. This is expected. And one more time here, if some details are not clear, do not worry, click on the link. You can read more detailed discussion of how these details are implemented. The main takeaway over here is these 2 points. When the notation is prefix, the first pop produces the left argument, the second pop produces the right argument. If the notation is postfix, it's the other way around. The first pop produces the right argument, the second pop the left one. It should be understood why. It depends on the direction, or the reason why these things work the way they do is based on the direction in which we parse the input. And now that we more or less understand how the Shunting Yard algorithm works, we can discuss its animation or a visualization, which I refer to as a slow motion player. As I mentioned earlier, I see at least 2 reasons why a computer science algorithm should be animated and or visualized. The first reason is that doing so will help us understand the inner workings of this or that algorithm. And I think that the overall approach to animation and or visualization of computer science algorithms is an endeavor that is worthy in its own right. It can stand on its own. And the reason number 2 is, aside from being a teaching or a learning aid for students of computer science, this is an ultimate test of our understanding of how this or that algorithm works, and the positive statements here are the following. If we do not understand how a computer science algorithm works, then there is absolutely no chance that we can come up even with a remotely reasonable animation and or visualization of it. And if we do understand how a particular computer science algorithm works, it doesn't really mean that we will, or it's not a guarantee that we will come up with a reasonable animation. It remains to be seen if we can animate or visualize such an algorithm in a reasonable way. Here my take, and this episode is not dedicated to the nitty-gritty of the Shunting Yard algorithm. The emphasis of this episode is precisely on an animation and or visualization of the Shunting Yard algorithm. This is my version. I hope that you can do way better than I did. I'm more than curious to see what you can come up with, but my idea is the following. Normally, when a computer science algorithm is executing evidently, and of course we want to this algorithm to be executed as fast as possible in one fell swoop in a non-interruptible fashion, but the idea of the slow motion effect of a particular algorithm is to allow a user to experience the step-by-step execution of this algorithm. In other words, a slow motion player should bring front and center this step-by-stepness of how the algorithm plays out in real time in front of the user's eyes. And my take here is the following. I did this in using the Java programming language, the built-in visual library that it had at the time. Again, the link to this software is in the comment section. Take a look. But my idea is the following. On top, I created the visual representation of the input queue. This is where we enter the infix expression, or this is where we enter the expression in the infix form. For example, our proverbial open paren 1 plus 3 close paren multiply times 5 plus 17 and so on. The result will be stored over here. Then we use the input using the input panel shown on the lower left. This is a minor detail, but here we have numbers on one side and the operators and the controls backspace and clear on the other, parentheses and whatever operators we choose to implement. Now, in the middle, I created the output queue. This is the mechanism of visual representation or an animation or visualization of how the expression given in the infix form is converted with the help of this convert to panel into either prefix or postfix notation. You decide as the user, as the driver of this slow motion player. You click on prefix if you want the prefix notation to be shown here, or you click on postfix if you want postfix. These are mutually exclusive. You cannot select two, one at a time. And the animation and the slow motion effect of this algorithm, the way I achieved it is I slowed down this algorithm into running in the step-by-step fashion by using the next button. Every time you click next, the next step in the parsing, for example, in the first stage will be carried out, and the output queue will be populated. You remember, it will be populated left to right or right to left, depending on your choice of prefix or postfix. And once this process is complete, the convert to panel will be disabled. This panel will be enabled. Initially, this panel is disabled because we do not compute, we first convert. And during the conversion process, you can see exactly which input item or which input token is worked on, left to right or right to left, and you see how the output queue is populated. You'll see how the stack is used with the operators. The whole idea is to, again, visualize or animate a stack. Maybe it's not very successful because my stack is located horizontally. Usually we like to show it vertically, but for space requirements, because the real estate is quite hungry in this case, I decided to roll the stack horizontally. Maybe you will come up with a better idea. Now, once the conversion into either prefix or postfix notation is done, and this result is stored in the output queue, depending on your choice, prefix or postfix. Again, like I said, the control panel is disabled, the compute panel is enabled, and here the second stage, you execute the second stage with clicking the next, next, next. And as you click every time on the next, 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 the second stage of the algorithm is animated. The input queue is processed one at a time. The arguments are placed on the stack. The right argument is placed in this box over here. The left argument is placed over here. This is the operator box, and this is the result. The result is pushed back onto the stack, and once you compute the entire expression is evaluated, the next button will become disabled, and the result will be shown in this box over here. So the material given in the Infix form, result produced over here, and the fun of this project, for me at least, was to create the slow motion effect by slowing down the algorithm, which normally zips through the input, produces the intermediate precompiled form, postfix or prefix, and then zips through the postfix or prefix form, rolls through the stack, and produces the result in one fell swoop. Breaking this down is an interesting part. I recommend that you try it on your own. Like I said before, let me write it down for you over here. This was written in Java. It provides, back in time, it provided a reasonable graphical user interface library. All these visual elements are not complicated. This is all standard stuff. Maybe these days you can come up with something better. Share your ideas, share your software with us, provide links to your probably GitHub repository. I'm curious to see what you come up with. But again, this is a worthy exercise. Once you understand the nitty-gritty ideas, the mechanics of how the Shunting Yard algorithm works, this is a good way to break into the business of animation and or visualization of computer science algorithms. This is just one way, and I recommend that you give it a try. Our next challenge will be a problem in mathematics, S3M13, the 13th problem of season 3, and the statement of this problem is the following. Come up with at least 3 creative ways to evaluate these two integrals. The integral shown on the left, which is the integral of the exponential function raised to the power ax times the trigonometric function of cosine evaluated at the argument bx. The integration is carried out over dx, and the function sab of x that is represented as an integral of the same base of the natural logarithm e raised to the power ax times the value of the trigonometric function of sine evaluated at the argument bx. The integration is carried out over dx. We saw where these integrals come from. Remember when we were solving the problem in physics, when a point was executing a planar motion in such a way that it's both normal and tangential accelerations remained constant at the same time. We deduced with mathematical precision the shape of that trajectory, and in the process we came across precisely these two integrals. Find at least 3 different creative ways. The emphasis here on creative. Integration by parts is boring on this channel. You need to do better than that. Think hard, think of different things. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my 3 creative ways of evaluating these here integrals.